Stella Truman or Miss Janice DeWitt will be sending individual messages to everyone to gather your student ID numbers to sign you in. Without further ado, I'll pass it on to our presenter so that we may begin.
Hello, everyone. Hope everyone is doing well. Give me just one quick second. Let's say about 40 seconds, and then we'll start.
Hi, Mr. Asasi. Can you hear me?
Okay. So if you are in 1324, they have placed the link for you so that you can go to the other room for 1324. And if you're in 1314, then today we're going to be talking about synthetic division and complex numbers. At any time, if you have any questions, feel free to ask me. Okay, so in chapter 2, we're going to be talking a lot about zeros. And the zeros here, I have circled it. This 0 here is 2, 0. And if we notice here, we can say that x is equal to 2 as a 0. And if I subtract the 2 on the left side, then we have x minus 2, which is going to be called a factor. So each of these parentheses here, these are what we call factors. And if we set them equal to 0, each of them, then we get the zeros that are on the graph. That's where the x-axis crosses. So part of our goal today is going to be to find these zeros. And there's different methods. One method is to use long division, and then the other one's going to be synthetic division. And so I'm going to briefly show you both methods. My favorite is a synthetic division. I feel like it's a little bit quicker. And so here are the steps, and you'll be able to download this PowerPoint by clicking the arrow. If you see my blue arrow here, on top of it, there's a box with an arrow. You can click on that and it'll help you download the entire presentation. And so for long division, it works a lot like regular division. And so one of the first things you want to do is arrange the terms in descending powers. That's very important. And if a term is missing, we're going to be adding a placeholder, which is of 0. Okay. Then we're going to divide, and then we're going to multiply and subtract. And so I'll help you see this better when we do the example. Okay. So let me just skip through those steps. So here we have a polynomial, 20x cubed minus 35x squared plus 23x minus 6. And we're going to be dividing this by 4x minus 3. So the first thing we want to do is I'm going to rewrite this in this form. And I'm going to make sure that my exponents are in descending order. So here we have an exponent of 3, 2, 1, and then we have our constant. And the same with our divisor here, it should also be in order. So here I have a 1 and then followed by the constant. Okay, so the first thing we want to do is we want to divide the first two terms. So we're going to have 20x cubed divided by 4x. And so 20 divided by 4 is 5. And x cubed divided by x is x squared. And so I'm going to go ahead and write 5x squared on the top. And then just like if we were dividing regular numbers, now we're going to multiply 5x squared times 4x. Okay, so I multiplied it here. So 5x squared times 4x is 20x cubed. And 5x squared minus 3 is negative 15x squared. So whatever we get here, notice that I put it in parentheses because I need to subtract this information from the first two terms up here. And so always we want to remember that the subtraction or the negative here, we're going to distribute into the parentheses. Okay, so here I have demonstrated this. So we're going to have negative 20x cubed, and then negative and negative will be a positive x squared. And now we can go ahead and add those together. So 20x cubed minus 20x cubed is going to give us a 0. And negative 35x squared plus 15x squared is going to be negative 20x squared. And then we bring down the next term, in this case 23x. And then we're going to repeat this process. Okay. So for some of us, the long division is something that we prefer, and then some of us are going to prefer synthetic division. So now I start the same process. So we're going to take, let me see here. So I have this information, negative 20x squared. I'm going to divide it by 4x. So 4x times negative 5x is going to give me negative 20x squared. And negative 5x times negative 3 gives me a positive 15x. And so don't forget this negative out here. We're going to distribute it across. And so I'm right here in this line. So negative negative is a positive 20x squared, and negative times 15x is a negative 15x. So my first terms, if I add those, I get 0. And then 23x minus 15x will give me an 8x. I'm going to bring down the negative 6. And so now I start again, right? So I have 8x and I have a 4x. So what number do I need to multiply 4x to give me an 8x? That's going to be a 2. So 2 times 4x is 8x. And 2 times negative 3 is negative 6. But remember, since we are subtracting, we're changing these signs here. So 8x minus 8x is 0. And negative 6 plus 6 is going to be 0. Okay. And later on, when you get remainder of 0, that's going to make us very happy. Okay. So you'll see why in a few minutes. So once we have our division, let's talk about what these numbers mean. So the last number you get here, this is called your remainder. The stuff you get up here is called your quotient. And then what we're dividing by is your divisor. And then the inside here is called the dividend. Okay. So when you write your answer, we want to write it as the quotient plus the remainder divided by the divisor. So in this case, we have our quotient, 5x squared minus 5x plus 2, plus my remainder, which is 0, divided by 4x minus 3, which is really 0 again here. But I went ahead and wrote it this way so that we can, sometimes you will get a different remainder other than 0. Okay, so I think I have okay, I only had one example because synthetic division is actually a quicker way of doing long division. So synthetic division will work if your divisor is in the form of x minus c. Okay, so that's always important. It should be x minus c. We are going to put our terms in descending order. So the exponents are 3, 2, 1, and so on. And if anything is missing, for example, if cx was in here, then we're going to use a placeholder of 0. Okay, so the way this works is we write down our coefficients. So my coefficient for the first term is a. And then the second second term has a coefficient of b. And then the third one has a coefficient of c. And then we have d. Okay, so then we take our k. We take our k and we write it on the left side here. Okay, so that is the process there. Next, we're going to bring down the a, the first number, and we're going to multiply it times k. So k times a is ka. And then we're going to add it to the b. Okay, so b plus ka. And we're going to keep doing that until we finish with the letter d. So let me give you an example with real numbers. That way it's easier to work with. So the last number you do get is your remainder. And then the numbers before that are your quotient. So let's go ahead and do an example. So in this example, what is k? So here's my dividend and here's my divisor. So we're trying to find out what k is. So k is going to be 1. So now our next step is to write down our coefficients. So in front of x squared is a 1. And then in front of the x is a 5. And then we have a 6. Okay, so our next step is to bring down the 1. And then we're going to multiply 1 times 1. and that gives me a 1. And then we add 5 plus 1 is 6. And 1 times 6 is 6. And now we keep adding, right? So 6 plus 6 is 12. Okay, so our answers here, the last number is your remainder, and the numbers before it is your coefficient. So to write, your quotient. So to write your quotient, you're always going to start with 1 degree less. So if you notice here, this polynomial, the degree is 2 because the highest exponent is 2. Okay. So when I write my quotient here, this number 1 is going to have 1 degree less. And so here we're just going to get, so let me keep going here. So our quotient is going to be 1 degree less. So we're going to have x. So the 1 goes with the x. And then the 6 is going to be your constant. And then your remainder is 12. And then your divisor was x minus 1. Okay. So let's try another one. I think I have quite a bit of them here that we can practice with. All right. So k is 8. So I go ahead and write it there. Now I'm going to write my coefficients. So I have 4, 36, 36, and negative 32. My first step is to bring the 4 down. Then we multiply 8 times 4 is 32. Then we add 36 plus 32 is 68. And then we multiply again. So 8 times 68 is 544. And then we add the 36. So we get 580. And then we keep multiplying. So then we get 4,640. And we add negative 32. So that becomes 4,608. Okay. So in this example, which is going to be my remainder? So again, the remainder is always going to be the last number. Okay. And the degree of my quotient is going to be 1 degree less. So the degree of this polynomial is 3. So when we write our quotient, it's going to be starting with x squared. So we have 4 times x squared. The next number would be 68x. And then the next number would be 580. Our remainder divided by our divisor. Okay. So let's look at a different example. So here we have something similar, but the big difference is, notice that our divisor has x plus 7 instead of x minus a number. Okay. So we need to identify k. So I can rewrite x plus 7. I can rewrite it as x minus negative 7. So as in here, our k is going to be negative 7. So one of the things I like to tell students, you can look at this. You're always going to write the opposite. So if you have a plus 7, you write negative 7. If you have an x minus 7, then you would write a positive 7. Okay. So the next step is our coefficients. So we have a 3, we have the 21, the negative 6, and the negative 42. Bring down the 3 times negative 7 is negative 21, plus 21 is going to be 0, times negative 7 is 0. And at the negative 6, negative 6 times negative 7 is positive 42. And if we add, we get 0. Okay. So later again, as I mentioned earlier, if you get a 0 here, you're going to be super excited, right? And you'll see why, hopefully, either in this section or the next section. Okay, so my remainder is 0. Again, your degree is a degree 3. So when you start writing your polynomial here, you go 1 degree less. So we're going to have 3x squared. There's no term for the next one. So that would be the term for x. And then you would have your constant. So we have 3x squared minus 6. And then, of course, the 0 here is divided by x plus 7 is 0. Okay, let's try one more. So I'm going to give you about 30 seconds to maybe try it on your paper, and then I will show you what comes next. So first identify what x minus 5 is. I mean, what is your k? Okay, so I'll give you 30 seconds.
All right, guys. So let's continue. Yes. So what is it? What is different from this one that we haven't seen before? So we notice here on this particular one, um, we're missing a term, right? We have the x cubed minus 3x squared, but we're missing the x. So we got to account for that. And then again, we have a k. Um, since it's a -5, just like Ms. Chuka said, our k is going to be a +5. So we've know what our k is. It's going to be a 5, okay? And now we're going to put um, our quotient in, or excuse me, our dividend in. So again, we were missing an x value, so we're going to go ahead and put a 0 for that one. So we have 1 minus 3, 0, and 6. So again, our first step is bringing down the 1. We're going to multiply 5 times 1, gives me 5. So now I'm going to add -3 plus 5, which is going to be 2. Now I'm going to multiply 5 times 2, which will be 10. I'm going to add 0 plus 10 is 10. And then 5 times 10 will be 50. So I'm going to add 6 plus 50. It's going to give me the 56. So again, our last number here is always our remainder. So our quotient is going to be 1 degree less. We started with a cube. So now we have x squared plus 2x plus 10 plus our remainder, 56, over our divisor, which is x minus 5, right? So there was a little trick on this one. Awesome. All right. So let's go over what's called our remainder theorem. So if a polynomial f of x is divided by x minus k, then the remainder is f of k. So what this means is that the value that we are dividing with, when we plug that into our function, that's basically our remainder. It's what's left over, right? Um, so let's go ahead and look at an example using our remainder theorem to find our function value. So it says use the remainder theorem and take the division to find each function value. So the function that they're giving us is 2x to the third minus 7x plus 2. And what they want us to do is evaluate this at f of 1. Remember, so this is this value 1. We're going to plug it into our function everywhere we see x. So let's go ahead and do this first example A. Well, let's first do the synthetic division. So again, we're going to divide by 1, or k is going to be 1. Here we have 2x cubed. We're missing the x squared term, so we're going to put 0 here. So we have minus 7 plus 2. So when we do synthetic division, again, we go through the process, we end up with a remainder of -3. But check it out. When we do this and we plug this value into our function, we are going to get our same result. So when I plug in 1 to the function, 2 to the 1 cube minus 7 times 1 plus 2, when I simplify, I'm going to get equals -3. So again, our remainder theorem says that when we plug into a value into our function, this is going to give us our remainder, okay, just how the name sounds. So let's go ahead and do B. Um, let's start with doing the synthetic division for -2, or input value -2. So again, when I do synthetic division, I have a remainder of 0. So if I plug this in into my function, you'll see that my value for y will also be a 0. Or again, this is my remainder. Okay. So again, the equation for this is given by x equals -2 is our 0 of our polynomial. That means that this is where, again, if we're talking about graphing, it's the solution or where it crosses the x-axis. Yes? All right. Um, let's go ahead and solve now. Now that I gave you a hint that this is what it's leading to solving equations or finding zeros of a polynomial. Let's go ahead and find the zeros for this given function. 2x cubed minus 7x plus 2. And our problem says that we're given that x equals -2 is a 0. So what we want to do is let's go ahead and use synthetic division to simplify this polynomial, because this polynomial is a cubed. And in our arsenal to solve for polynomials, well, we have factoring and we have also the quadratic equation, but we don't have any. This could be difficult to factor, right? It's doable, but it could be a little bit complicated. But if it was a square, right? If it was a quadratic, we know how to solve for those really easy. So when we use synthetic division, and the fact that they told us that x equals -2 is a 0, I can use that to my advantage. And this is what Ms. Chuka was saying. That makes, when we have a 0 as a remainder, makes us really, really happy. Because it turns out to be a factor of our polynomial, right? So when we did synthetic division, we see that we have, right, big smile, Ms. Chuka, we see that we have a remainder here. But here, our quotient, if we write this as a polynomial, we're going to end up with 2x squared minus 4x plus 1. Again, what we notice is we are happy because it's a quadratic and we're able to solve for these very, very easy. And again, there's several things that we know now on how to solve for this. We can use factoring, we can use square root property, or we can use our quadratic formula, right, to find the rest of the zeros. So we have one of them. So I have a feeling that we're going to find two more. Okay, so let's go ahead and factor this. That's my option always. I love to factor these. So if I factor 2x squared minus 4x plus 1, this factors into 2x minus 1 times 2x minus 1. So if I see here, I have a double 0, right, which is the same value, 1/2. Our zeros for this polynomial are -2, the one that they gave me. Don't forget that one. Again, when you do these on the computer on the homework, don't forget that the one that they gave you. Okay, so my answers are 3 zeros, are -2, 1/2, and a 1/2. Okay, awesome. So that's why we like zeros for the remainder. So let's go ahead and expand this system to solve also this polynomial. X squared plus 1 equals 0. Okay, so if I were to use my square root property, first I would subtract 1 on both sides, and I would get x squared minus 1. X squared is equal to minus 1, excuse me. Take the square root of both sides, and if I see that if I take the square root of a -1, that is not a solution. Later on, we will see that they'll give us a value, but right now, there's no real solution. Okay, so then again, on this problem, on complex numbers, we have no real solution. So what does that mean? Well, what that means is that the graph is not crossing our x-axis. There's no x-intercepts, right? There's no values that give us a 0 for a solution. Okay, and then you see here, our graph on this parabola could be above the x-axis, or the parabola can be below the x-axis. But again, it's not crossing my x-axis. So that's what this means. No real solutions means that my graph is not crossing the x-axis. Okay. All right. So again, I hinted on this, but what this produces again, and we will be seeing this in this coming chapters, or if not, you've already seen it in your classes. When we take the square root of a -1, this one is going to produce an imaginary number. And that imaginary number, we like to indicate it as I, okay, I for imaginary. So again, if I were to take the square root of -1 and square it, I would get just the value of -1. So that leads to this interpretation. I squared is going to be equal to -1. So -1 is considered a complex number, and we will be dealing with complex numbers in standard form. And what standard form means is that it's going to be a number composed of a real part and imaginary part. So our complex number in standard form, just general equation is given by a plus bi, where a is the real part and bi is the imaginary part. Okay. So again, let's look at the formal definition of a complex number. And it says that the definition says, let A and B be real numbers. The numbers A and B is a complex number when written standard form. Okay. So again, as I mentioned, A is the real part and the BI together is the imaginary part. Okay. So the definition did say that A, B are real numbers. Oh, again, these are real numbers, but when I combine it with BI, as together, this is my imaginary part. Okay, so just be careful when you're answering questions that deal with complex numbers. You always write them in standard form, real plus imaginary. Okay, all right, so let's go ahead and look at operations with complex numbers. Okay, so hopefully these are super easy. So when we're looking at the sum of complex numbers, the way you want to think about or look at the sum of complex numbers is by adding what's like terms. In other words, we're going to add real with real and imaginary with imaginary. Okay, same thing with the difference. If I were to subtract two complex numbers, the way I would do that operation is subtract the real with the real and the imaginary with the imaginary. Okay, so to better see these, let's look at some examples. Okay, so it says perform the operations and write the result in standard form. Okay, in standard form means real plus imaginary. So the first one, A, we want to add these two complex numbers, 3 plus I plus 6 plus 5I. So what I will be doing, again, I'm going to be adding the real with real and imaginary with imaginary. So my real parts here are the 3 and the 6. So I'm going to add those two together. My imaginary parts are going to be the 1 and the 5, and I have them here, right? So when I simplify, 3 plus 6 is the 9, the 1 plus 5 is a 6. Okay, so my complex number in standard form of this addition is 9 plus 6i, right? Hopefully really straightforward stuff. All right, so let's look at combining the like terms. Okay, so this means I can go ahead, since I have a plus, I can drop the parentheses, and again, I can add all these numbers together, but I need to add like terms. Just again, the real with the real and the imaginary with imaginary. So the 3 would be added with the 6, giving me the 9. The I would be added to the 5, giving me the 6i. Again, I like this format, but again, it could be a little dangerous because we might want to give the answer just however we write them. And in this format, again, if we follow this operation that we add the real with real first, then the imaginary with imaginary next, we already have it in standard form. Okay. All right. So let's go ahead and perform this operation. Now we have a subtraction. So we have to be careful because if you see here, we do have a parenthesis. So it's technically, we have to distribute the sign and add the two complex numbers, right? So here, my real minus imaginary is going to give me the 3 minus 2. And then the imaginary minus 1 plus times a negative is going to give me a positive, right? So we have a minus times a plus is going to give me a 0 for the imaginary. So when I add these together, the answer could just be 1. But again, we got to be careful. The standard form, sometimes the computer might not accept this. It wants it in standard form, and we might need to write that 0i. But I don't think so. I think I'll accept just the 1, but it's a good habit to always write things in standard form, 1 plus the 0i imaginary. Okay. Again, the second method is just distributing the negative and then combining all the like terms. I distribute the negative with a 2, gives me a negative 2. A negative times a negative I gives me a positive I. So the 3 minus 2 is a 1, minus I plus I is a 0. Okay. Ooh, how about this one? Perform the operation and write the result in standard form. Oh, I like this one because this one we have to do a little extra work, right? So when we started dealing with complex numbers, we noticed that when we had the square root of a negative 1, that's what gave us the I, and that's what's missing in these problem here. We don't see an I, but it is there because we have a square root um, with a negative number. So to do these, what I like to do is I like to break up the square root with the negative number inside. So what I do is I like to break that up into two parts. The way I get negative 8 is by multiplying a negative 1 times 8, right? And by me doing this, you'll see why. But let me go ahead and split up the other one, the negative 56. The negative 56 can be written as negative 1 times 56. And if, again, if you recall, when I take the square root of a negative 1, that produces the I, right? So here, if we have these values, again, we're using just the full formula where negative 1 is equal to I squared. So that's what I'm going to replace these negative 1s with. 2 plus the square root of I squared times 8 minus the square root of I squared times 56. So again, um, if I continue simplifying here, I am going to end up with the square root of 8 stays inside, but the I squared taken to the square root gives me just I. Over here, the same thing, minus the I squared to the square root just gives me I, goes outside the radicand, and I'm left inside just with the square root of 56. So now I can see that I can combine my like terms. I have two terms that have an I in them, right? So when I simplify this, the square root of 8, it's 4 times 2. The square root of 56 is 4 times 14. Both of these have a perfect square, which is the 4, right? So now I have two I square roots of 2 minus 2 I square roots of 14, okay? Which simplifies to 2 plus, I'm going to factor out the I, okay, and leave me these two. Since they're not the same radicand, since they both don't have the same square root, I cannot add them together. So I'm just going to leave them separate as they are. It's 2 square roots of 2 minus 2 square roots of 14. So again, also another thing to be mindful. Okay, the computer for these problems wants the exact answers. Don't use a calculator to evaluate the square root of 2 or the square root of 14. Leave the answers as they are because, again, they want the answer in standard form. This is the real part, the 2, and my imaginary part is this, the I, 2 square roots of 2 minus 2 square roots of 14. Now, also, another thing to keep in mind is it doesn't matter if you put the I in the front or in the back, okay? Um, one of the things you can do is also excuse me, I was reading the chat. Yes, Jesus, you can factor out the 2 as well. That would be fine. They wouldn't count that wrong. So what I was going to mention, the reason why they like to move the I to the front is that you're careful not to put the I inside the radicand because sometimes we want to put the I at the end, but we extend the square root over the I, and that would make that problem wrong, right? When we took the I squared, that I went outside the square root, so it's no longer inside. So to help us, that's why they move them to the front, okay? But if you put them to the front or the back, just make sure they're outside. But great, thank you, Jesus, for letting us know. You can factor that 2 out and it would be correct as well, okay? All right, let's look at this example. This is different. This is not addition or subtraction. This is now a multiplication of two complex numbers. We're going to multiply 1 plus 5i times 8 minus 7i, okay? So on this one, there is no basic rule that we don't already know. To multiply these two complex numbers, what we're going to be doing is we're going to be doing FOIL. Okay, so to do this operation, what I need to do is I need to multiply the 1 times both of these two terms that are on this side times the 8 and times the minus 7i, and I need to multiply the I times the 8 and the minus 7i. So let's go ahead and do that. Okay, so when I do that, 1 times 8 is 8. 1 times a minus 7 or negative 7i is a negative 7i. Now the I times 8 is a 8i. And positive 8i times a negative 7i is going to give me a negative 7i squared. Okay, so the first thing that I can do is I can combine my like terms. Okay, or well, before I do that, I know that I squared, again, from our definition, I squared means that it's a negative 1, right? So here I did combine my like terms, A negative 7i plus 8i is just a positive I. And then again, I have the minus 7, but the I squared was a negative 1. So a negative 7 times a negative 1 is a positive 7. So I'm left with 8 plus I plus 7. Now I have two more like terms. Now I have two real numbers, the 8 and 7. So 8 plus 7 is a 15. And I got to make sure that I write this in standard form. My real part is the 15 plus my imaginary part, which is the I. Okay, so this was an example of a multiplication of two complex numbers. And to do this, all we need to do is FOIL. Okay, all right, let's go ahead and do one where we're doing multiplication, but it's basically just we're distributing the 17i to this complex number 1 minus s7i. So let's go ahead and do this. We're going to distribute the 17i. So 17i times 1 is just 17i. A 17i times a negative 7i is going to give me a negative 119i squared. Okay, now we know that I squared is a negative 1, so we're going to go ahead and replace that. Our I squared became negative 1. So now we have negative 119 times a negative 1, which is going to give me a positive 119. And are we done? No, we want to rearrange this because this is not in standard form. We have the imaginary part first, and then we have the real part first. So we got to swap them when we put our answer into our computer. So our answer is 119 plus 17i. This is standard form, real plus imaginary. Okay. All right. So again, this is our standard form. All right. Now let's do another example. Let's do one that has division, right? So to write the quotient in standard form. Okay, so we're basically just asking us to write it, but we're doing this operation. But let me tell you, there's no such thing as really a division of complex numbers, but we do know how to multiply complex numbers, right? So in order for us to do this, I need to introduce a new concept. For me to do this operation or to be able to write it in standard form, I need to multiply the denominator by its conjugate. Okay, so what is its conjugate? So to identify the conjugate of the denominator, it's really easy. Okay, so I see that I have a complex number here at the bottom, which is 5 minus 6i. So the conjugate of 5 minus 6i is the opposite sign of this operation. So I have a 5 minus 6i, so its conjugate is 5 plus 6i. Okay, so look what's going to happen if I do this. If I multiply both the denominator and numerator by this conjugate 5 plus 6i. So when I do that, I'm going to multiply and I'm going to apply. Again, whatever I do at the bottom, I need to do to the top. So I'm going to multiply 5 minus 6i times 5 plus 6i and 3 times 5 plus 6i. And I'm not really changing my problem because what I'm really doing is I'm multiplying by 1, right? 5 plus 6i divided by 5 plus 6i, that's just 1. All right, so the top is fairly easy, right? It's just distributing the 3 times the 5, 3 times the 6i, and then on the bottom we have again a FOIL operation, which we're going to multiply 5 minus 6i times 5 plus 6i. So if we go ahead and do this and simplify, again, the top is super easy. 3 times 5 is 15, 3 times 6 is 18i. Okay, and then the bottom, after I do FOIL, I have 25 plus 30i minus 30i minus 36i squared. Okay, so I'm going to combine my like terms. 30i minus 30i, that gives me 0, leaving me with just 25 minus 36i squared. But I know that I squared is -1, so let me go ahead and replace that. Um, so I have 25 minus 36 times the -1, which is going to give me a positive 36 after I multiplied the negative 36 with a -1. So now I can add these two numbers. 25 plus 36 is 61. So if you notice, when we multiplied the denominator by its conjugate, we got rid of the imaginary part. We no longer have an imaginary part. So now, since I have a term that is being divided by one single term, I can separate it into two fractions in order for me to have it in standard form, right? So I'm going to divide the real part, 15 divided by 61 plus 18 divided by 61i. And if you notice here, we have it now in standard form. We converted 3 over 5 minus 6i into its standard form of 15 over 61, the real part, plus 18 over 61i, which is my imaginary part. And in order for me to do this division, or to write it in standard form, I need to multiply by the denominator by its conjugate. All right, so let's see. Do we have one more example? Yes, awesome. All right, so here we have write the complex number in standard form. So we don't see any i's, but what we do see is we see negative numbers inside our radicand, right? So we know that we are going to have an imaginary number. So first, our solution, again, what I like to do is separate them to take out my -1. That's going to give me that I value, right? So I do -1 times 75, okay? And then I do -1 times 12. Now, I'm going to replace of what -1 is. I know that -1 is the I squared, so I'll replace them with I squared for both. And then I know that if I take the square root of a square, I can take out the I. So we have I times the square root of 75 plus I times the square root of 12. So let's simplify. Let's simplify the square root of 75 and the 12. Okay, so here what I do is I have 25 times 3 will give me 75. And then I have 4 times 3 gives me the 12. Okay, so our goal is to end up with the same radicand. Okay, so now um, one of the things that I'll do, leave it at the end. I'll give you some examples on if you don't see these multiplications. I can show you a different way on how to simplify our radicands. Okay, so again, I wanted to have a 25 because I know that has a perfect square, and I wanted to have a 4 here because I know 4 is a perfect square. So when I simplify this, the square root of 25 is 5, so that goes out. The square root of 4 is 2, so that goes out. So now do you see that I have the same radicand? The fact that I have a square root of 3 with a square root of 3, this means that these two are like terms. So now I can add the like terms and keep the radicand. So what I'm going to do is I'm going to add 5i plus 2i. It's going to give me the 7i. And I keep what they like. They're the same, the square root of 3. So think of the square root of 3 as it being x, right? If I have 5x plus 2x, I'm just going to add the numbers and then I keep the symbol, right? It would be a 7x. So in this case, it's the same thing. I have the square root of 3 is what they are, the like term. So I'm just going to add the outside, the 5i plus the 2i, again, giving me the 7i square root of 3. Now, I need to write it in standard form. This is just the imaginary part. So in standard form would be the 0. I don't have a real part. 0 plus my imaginary part, which is this, 7i square root of 3. Okay. All right. Let's see. Do we have one more example? Okay. We can use quadratic formula also to solve these. And again, before we had it easy in chapter 1. Whenever we had a negative number inside the square root, we just said the answer does not exist. But now we know that there is something that exists, and it exists an imaginary number, right? So let's go ahead and use the quadratic equation to solve this polynomial. So we know that in our polynomial here, a is 1, b is -2, and c is +2. So let's go ahead and apply our quadratic equation, replace our variables. So we've done this here, okay? And let's go ahead and simplify. And when we simplify, we end up with this, a 2 plus or minus the square root of -4 over 2. So again, no more we have answers of do not exist now. Now we're going to have a complex answer, right? So again, we can do the same thing that we had done before, okay? We can separate this -4 into a -1 times a +4. I know that -1 can be replaced by the I squared, and when I take the square root of that, it's going to take out my I. Okay, so I'm going to have 2 plus or minus I to the square root of 1, right? So which is just, sorry, 2. So it's going to give me 2i. So I have 2 plus or minus 2i over 2. Okay, again, I have two solutions, and again, we need to write these in standard form. Okay, so let me go ahead and separate them. Okay, in standard form, 2 over 2 plus or minus 2i over 2. So my two answers, 2 divided by 2 is 1, plus or minus 2 divided by 2 is 1, so it's 1 plus or minus I. Now let me see if I wrote it here. Yes. So on WebAssign on the computer, there is no symbol for plus or minus, okay? So when they ask you to give the answer as a list, let me get my pen out. The way you're going to answer them is like this. X equals, okay, they might write the X already there equals to. The way you want to write them on the computer is going to be 1 minus I, comma, 1 plus I, okay? Because again, there is no plus or minus symbol on the computer. So they want you to do a list, and it'll be separated like this. So I do have two solutions. Again, and we wrote them here. We have them as x plus I and x equals 1 minus I, yes? All right, so let me go back. Let me go back since I have a little bit of time. Actually, we finished a little bit quick. Let me go back to um, this problem over here. Okay, so let's say that you don't recognize the 75, or let's say let me see. Um, what if we had a number like this? Um, let me have more space here. Okay, so let me do this. Okay, what if I had a square root like this, negative, I don't know, let's pick something large, 248, okay, I don't know, and we need to simplify this, okay? So one way that I would do is, again, the first thing that you would want to do always is separate this into -1 times 248. Okay, you always want to take out that -1 because we know that that -1 produces our I outside. But again, maybe some of us can look at the multiples of 248. So remember, square root means we want to make pairs of numbers. So what I would do to simplify this, because the computer wants me to give exact answers, what I would do is, oops, 248. What I would do is a prime factorization tree to be able to get the multiples of 248. So in order for me to know what I need to factor out. So again, just to recap, a prime factorization tree is you want to divide this number 248 by its prime number, right? So, and I want to get the multiples of all the prime numbers, the building blocks of 248, right? So 248 is an even number. So its first prime number is 2, right? So what I'll do is I'll divide 248 by 2. And this is going to give me 1, 2, 4. 2 times 124 will give me the 218. Okay, so 2 is a prime number, but I see right. So, Jesus, you got it down packed, right? You see that 4 um times 62 will give me the 248. But some of us, we don't see them, right? So what I'm doing is I'm taking it to the building blocks. If you see it, that is awesome, right? And hopefully we can, and with time we will. But in case that you don't, okay, this is a good way to do this. All right. So then I'll do again. I have a composite number 124, which is still an even number. So I'm going to divide this by my first prime number again, which is 2. So 2 divided into 124 is going to be 62, which is what Mr. Mata already had, right? So again, 2 is a prime number, but 62 is still a composite number. It's even. So I'm going to divide again. Can I divide this again? Let's see. By 2. So 2 divided into 6 is 3, and 2 divided into 2 is 1. So um, now I have all the building blocks of 218 because 31 is a prime number. I cannot divide 31 anymore. Even though it's an odd number, it's a prime odd number. Nothing is divisible by 31 except for 1 and itself. So the building blocks of 218, if I grab the leaves of my trees, I have a 1, 2, 3 2s, and the 31. So if I were to write this inside the radical, and again, I have an I that came outside, and I have the square root of 248. The building blocks of 248 are 2 times 2 times 2 times 31. Okay, so again, it's all about making pairs of numbers. So I have a pair of 2's that can come out. So that's the 2i. And then inside, since these two don't have a pair, I would multiply them back together. So that would give me my 62 that I had in front. Okay, so this is a great way that if you don't see the multiples right away, you can do a prime factorization tree to simplify the exact answers of these radicals. Okay, do we have any questions? Ms. Chuka, would you like to add anything?
No, just next week we'll be covering, I believe, finding the zeros, which is, um, uh, in my opinion, I really like that section, but sometimes students seem to struggle a little bit with finding the zeros. So hopefully we'll see you all here and have a great weekend.
Thank you, Ms. Chuka. Thank you, Mr. Carizales, for your presentation. If you would like to download a copy of the presentation, you can go to the top right corner and click on the box with the arrow going down while the presentation is on the screen. That'll allow you to download the presentations. And we do want to remind you all about the previously recorded sessions, which are available on the YouTube playlist. This session will also be available on that playlist a little later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and remember to send your student ID number to us before you log out. Before you all leave, I want to share the TVE sessions that we will have next week. Okay, there we go. So at 1 p.m. today, we will have a presentation on diabetes prevention with Irma Montoya. Join us again next week at 11 a.m. for Happy Math Hour, where Math 1314 will be covering finding zeros of polynomial functions, and Math 1324 will be covering simple and compound interest annuities. Our 1 p.m. session on that day will be exploring a career in libraries. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or your mic. We hope to see everyone again next week for Happy Math Hour.